Welcome everyone. This is Michael Hicks. I'm your instructor for Business Administration 602. This is a retaping of lecture 6.1.2 and 6.1.3 together for the single 6.12 file for the fall of 2020. This is a replacement for two broken files that are on YouTube that for later classes you won't see them. This will just be the single lecture. And so what we're going to do is just walk through a single file today and walk through multiple regressions, and then I'm going to introduce the questions that I'm asking in the practice exam one. So with no further ado, let's slip right over to the material to be discussed. There. This is the course material for the end of the material that we're covering for the first examination. So this is a file of multiple variables that are used from a recent study that I've had for Indiana. This is often what they look like at the county level. So you have state FIPS, that's a federal identification code for our state, the name of the state, the county FIPS, so you can see they all begin with the state FIPS 18001. It's very common to have data that are encoded this way. County name, total population in 2010, the wage in 2010, the median age in 2010, the total households, these are measured households in the county, the per capita wages in the county, that's total earned wages divided by the number of workers, the number of housing units, so this is the supply of existing homes for individual families or apartments, and then something called the Home Price Index 2010 with a 2000 base. The Home Price Index is a relative price of housing that's compiled by the Federal Housing Finance Authority, and all of this is available in the key. Right? So let me just give you some housekeeping tips. The first thing I like to do is I create a copy of the file, which I've done here. So I just label that working, and that file will provide me a place to change variables if I need without corrupting that original file, and then I'll just simply save this. And what I'm going to walk you through today is an extension from the linear regression models that we've done before that look a lot like this. So let's say I want to see how wages, wages per capita and the relative price of homes stack up. I would want to insert a graphic, right? And I can see there's correlation there, right? Or at least some clustering here, all right? Let's say I wanted to look at something else. Let's say I wanted to see if the number of the population, or let's say better yet, the number of total households align with housing units. So I would select that data from here, total households and housing units, and I would take a look at that, and I would say, gosh, we see a very strong correlation between the available homes here. So this is the explanation of housing supply and housing demand, and I would wish to format this trend line. You can choose to model it different ways, log or a polynomial. This looks linear to me. I can look at the equation on the chart, right, to see how the relationship is. So by the way, this 1.14 is essentially how many X here is going to be the left-hand side variable, so that's total number of households, and housing units are going to be the Y variable. And so for every one increase in number of households, there's going to be a 1.14 increase in the number of housing units, right? So oftentimes there is a value in making these comparisons, and not totally critical in this instance, right? And then as we've discussed before, when you're looking at this single univariate comparison or just a bivariate regression, I'm looking at how housing units and households match. I can look at this R squared, so 99.91% of the variation is explained by that. The problem with this regression is it doesn't tell us very much that we would really want to know about the relationship here. We're interested, for example, I might be very concerned with home prices. And I would want to know, as I've done before, let's say I want to select data. I want to see how home prices are affected by the median household wages, right? And I can see that there's a small negative relationship here. Well, that doesn't make sense by itself, does it? It doesn't make sense that home prices are going to be lower when wages are higher. Let's see if there's some relationship between wage per capita, right? So we'll look at wage per capita and house price index. Well, there's a positive relationship there. That makes sense to me. But the problem in economics or any data analytics that you do in marketing or finance is that it's very rare that a single variable will tell you what you need to know about the problem that you're trying to understand. And so what we might wish to do instead is to do a multiple regression. And let's look first at data here. We'll select data. We'll go to data analysis. And recall what I've asked you to do this, and just to restate that, is if you don't have this, you want to go to File, Options, right? And you want to go to Add-ins, right, down here to Excel add-ins, and you want to click the Analysis Tool Pack, and that will give you a lot of tools that you could otherwise construct yourself, but you'd like to go ahead. There's also Euro Currency Tools, which are converters, Analysis Tool Pack, and then a solver add-in. That would be used in some of your perhaps managerial economics courses. So I've added this into the data manager, and this gives me a variety of different things I can do. I can do analysis of variance, which will give me the relationship across the variance of these values. That's something that's used often in survey data. And so these three will be important for you there. There's basic correlations that we could compare two variables just to test whether or not means are different. And these are things that you'll learn, again, quickly in your statistics class, and you'll want to read the book carefully. I'd encourage you to keep the book with you. And then there's regression. Regression is going to be the workhorse of most of your business classes. And the single regression is that single plot that I've showed you before, but we're going to go to multivariate regression because we're interested from here on out in how multiple variables affect a single variable, or how do you affect this. So we're going to walk through this very slowly to try to understand it. And so in this case, I've done this before, but we're going to just you want to click labels so you don't lose yourself. Pick an output range that's nearby that you can see, right? So let's just pick this N1 here, so we'll get to see that. So the first thing I want to do is I want the Y variable to be price, right? So I'll choose price. I'm going to make some mistakes along the way just to practice this. And I'm going to look at wage per capita and see how that works. And so we'll run that first regression. Okay, so the first error is that you really want to pick just the variables. You can't do the whole column. This is a finicky add-on, right? Now, wage per capita. And we'll run the regression. And this is going to give us regression output. And so what I'll start by doing is I want to point out you're going to get an R squared, right? And the multiple R squared doesn't tell us very much. So we're going to highlight that. That tells us that 3.2% of all the variation in the data are explained by this the single variable that we have. So that doesn't explain very much. We have an adjusted R squared, which is a penalizing tool that reduces the goodness of fit based upon the number of variables you use. Because from here on out, as we add variables, that permits us to increase the R squared, but we want to penalize ourselves for just adding variables willy-nilly. That has been the argument. So the adjusted R squared is the more often reported variable in many of these evaluations. Economists don't worry too much about it, but it's a sort of a big issue elsewhere. And so then we're going to come down here, as we've talked before. We have these variables. First is the intercept. So the intercept is at 107. That is the univariate intercept that we saw when we graphed this before. And then the intercept can sometimes have value. In this case, I can't see much. We include it so as not to bias the results, but it doesn't. There's nothing informational about it. And the wage, the coefficient here, right? This is the coefficient. That's a value that tells you that for each each dollar increase in the wage per capita changes that index by 2 1,000ths, right? So that makes sense. There's a very big scale difference between the two, just sort of useful to understand. Then there's the standard error, which is very small. This is the signal, and this is the noise ratio I've talked about. And here's the t statistic. Remember this, as it approaches 2, it's statistically significant, and there's the p-value of statistical significance. That is at the 0.08 level. So this doesn't tell us a lot, but let's save this and put it in another worksheet so we can make comparisons along the way. And let's go back, and we'll erase that and do another regression here. All right, so now I want to do data analysis, and I'm going to do a regression, but this time I'm going to keep the same dependent variable, the same y, and we're going to add wages and household units here. We're going to have 2 variables in this, and I'm going to hit OK. Now I'm going to go through this again, right, and I can see that this increases that r squared. It almost doubles it, right? This F statistic tells us if that, I didn't cover this last time, if that's a statistically significant regression. If this isn't over about 2, the regression itself is of no value. And this is the overall signal of this entire regression to noise ratio, right? So the F statistic is the signal to noise ratio. And then we can look at these. So again, this looks very much like what we saw before. Very significant, but there's not much interpretation. The wage looks like we saw before and is even more statistically significant with this second variable in it. Okay, well, I'll talk about that. And then we have number of households. That's a negative value, but it's not statistically significant. So let's capture this and walk it over to the next page and make a comparison here. So now you can see here's wage. You can compare these 2 numbers. They're not far off, but this is more statistically significant. So we're getting some interesting results here. Let's go back and run another regression and see what we can find from that and what it might potentially mean for us. So we'll go to data analysis. We'll go to regression. We're going to keep that same home price index on the left-hand side. And for the X range, we're going to have housing units, wage. And now let's add another variable, total number of households, right? And so that gives us, and will give us the same out. Oops, sorry, I can't do that. So I'm going to keep that same variable. And now I'm going to input range these 3 variables. One of the finicky parts of Excel is that the variables have to be contiguous in the worksheet to work here, right? And so you may have to move things around, which is why I like keeping a spare spreadsheet. All right, so this doesn't improve the goodness of fit. Again, this r squared is the goodness of fit, and this tells us that about 5.5% of the variation in the data is explained by these 3 variables. And now we have a p-value for total home that's not statistically significant. That's not at the 10% level like this one is. So wages are statistically significant, but the housing units and the total number of households just don't matter. So let's snapshot this and take it over and compare it to these other variables. And so what we're beginning to see is that wages matter across the board. And why is that important? Well, intuitively, it makes sense that the average wages in a community are going to affect home prices, right, higher, and that's a positive value. And whether or not it's small or not kind of depends upon the units that we're using. So we're just using a home index, and so we in these data we're not looking at actual home prices, but an index of home prices. So it really tells us that the index value goes up. And an index value is just we take the averages, we compare them, and then we align them to 100 just to give us a snapshot, a comparison snapshot. All right, let's go back and just do another regression, and we'll do a little bit more fully and figure out what it is we want to, how we want to talk about this work. We'll go to data again. Go to data analytics, and again there's a lot to choose from. Go down to regression, right? I'm going to make another mistake for you. We've got the same dependent variable here, right? So we'll do those three, right? Then I'll hold control and I'll go to total population. And I'll run my regression. So it must be a contiguous reference. So I've made that error here. So let's just go ahead and just for fun, we'll just add all of these variables to it. Housing units, total population, wages, the whole 9 yards, and make a comparison. Everything else is the same. So here we have an R-squared that's gone up to 0.5, still not very high. Adjusted R-squared is lower, and the reason for that is that we're taking some, I don't want to go through the math of this because it's produced in every piece of software, but essentially every time I add a variable that is not statistically significant, it subtracts away from us. And in fact, this case, the entire significance of this regression is no longer any good. All right, and so what we have here is wage that doesn't have a p-value that matters. That's the total wage. Median age of the homes don't matter. Total households don't matter. Housing units don't matter. But this value, the wages per capita, continues to have statistical significance. And again, what we're looking at is if it's at the 0.10 level, we call that the 10% level, right? Recall the statistics. The 0.05, we're calling it the 5% level of statistical significance. And if it's at the 0.01, it's at the 1%. So these values here are like, far, far away from statistically meaningful, right? So we would not worry about those. Those are statistically indifferent from 0. And here's where a statistician and economist would vary. A statistician would pretend that these thresholds mean something. They don't. They were arbitrarily chosen by a quality control engineer at Guinness Brewery in about 1905 because he was sampling vats of Guinness beer to ensure that they were identical. And he drew vats of beer and he measured content in them, their ABV, the alcohol by volume, and other things. And of course, each vat, depending on how good your instrument is for measuring these things, each vat's going to have different levels of content. So he just wanted to, so what he would do is go to the same vat so that he knew everything was identical and just take random samples from the same vat. And he found they differed. And he wanted to come up with a mechanism to describe differences that mattered and differences that might not matter. So he was interested in seeing if differences in these ABVs at beer mattered across the same vat. So he found a way of measuring signal to noise, and the noise is really a measure of variance. And in much of the statistical work in physical sciences, medicine, and elsewhere, this is a measure of how good your instrument is, how good is the tools that allow you to measure temperature or volume. And then in the other sciences, it's may well be an equally good measure of that instrument, because how well did we measure the number of homes in a county? How many did we miss in a census? How many households or how many people did we miss in a census in 2010? Or how far off are we by wages? So the fact that we're actually measuring these things with a fairly blunt or poor instrument, far less precise than someone pipetting Guinness beer into a beaker to test the amount of alcohol that's in it by burning it or some other chemical treatment. So we're not physical scientists here in the business school, but our instruments for measuring the things we care about, from everything from revenues and costs to total number of employees in a given year, all those things are measured imprecisely. And so the tools of measuring the precision of our actual instruments are reflected in the way we look about the estimates here. And so there are different types of measuring p-values or t-statistics. That's actually named a student's t-statistic, because this Guinness brewer wanted to share his information with the world in a scientific journal, but Guinness was afraid that other people might steal their methodology and take, in part probably because it would take the mistake of Guinness away from everyone, and so he had to publish it anonymously as a student's tea, and it remained anonymous for some time. But this is one of the more important scientific achievements of the 20th century, was developing a signal-to-noise ratio, which allowed us to value things. And so very pure raw statisticians will care very much about these thresholds of 0.05 or 10%, but in reality, he just picked them randomly. It could have been 2, 4, 6, or 4, 8, and 12 as well. So people who are in business or people who are economists are measuring. We care an awful lot about this side. So a big value over here that's at a point. Let's say the wage premium was a 0.1. and the number of housing units was a 0.0003, and this had statistical significance at the point 0.00 0.012, sorry, 0.012, right? So this is the coefficient, and this is the t-stat. Next door to it, or this is the p-value, I'm sorry, derived from a t-stat. If that was at the 0.12 and this was at the 0.001 or 0.009, right, then a statistician would say, I'm sorry, 0.09, would say, oh no, that's good at the 1% level. And this one is not different from zero if I care about the 1% level. An economist would say, but look, the impact there is tiny. That's 3 out of every 10,000 occasions, or 3 out of 10,000 units, and that's 1 out of every 10 units. And so we would care deeply about the magnitude of the effect. So you'll see in economics classes, if it's instructed the way I would, that we would care a great deal about the coefficient values that we have in these areas. Okay, so now let's talk about combining these together to think about how all of these work. So I'm going to just stick it here so we can be I don't have to move around screens as much. Although evidently I'm going to have to make some move. So you can see across all of these different specifications, right, that wages matter. And again, what I did here was draw, I have a labor demand and a housing demand and a housing supply model where price is going to be equal to a function of wages and households, right? That's a, and et cetera, we'll call that et cetera is X. That's a labor demand or a housing demand. And here a housing supply is going to be equal to a function simply of that one variable, total housing units, right? And so I've made a reduced form model where price is equal to a function of all of these: wages, per capita wages, median age of household, total housing units, wage per capita, and housing units. Then these reduced form equations are very often used simply to provide a more forecasting type model. So if I wanted to know the effect of wages on prices, I would use an equation like on home prices, I would use this, and housing supply here on prices. But oftentimes I really care about where they intersect. As I showed you earlier, there's a pretty strong correlation between housing units and number of homes, so I would care about that if I were looking at supply. But in this instance, I'm really interested in seeing how prices are affected by all of these. And so reduced form models are very common in most business applications. Economists get a little worried about it because we're very theory driven. But in practice, in business, if you're trying to predict home prices or how many homes will be built, these reduced form models tend to work extraordinarily well. And that's really the benchmark for the statistics that we use in business. Are they answering the questions you're asking? Are they asking them with enough precision? Are they confident? Can you be confident that the things that they're telling you are useful? And that's really what this is about. And so you might build a model, then you might take it and you might build it on a subset of your data. So for example, I'm just showing you the Indiana data for ease of exposition, but I have all 49 other states as well. So we could build a model and then see how close it works in other states as well. And that would be a useful test of the model. And so that's really what business applications of statistics come down to is this telling us what we want to know? And so what does this equation tell us? So it really tells us is that the price differences of homes, really the index difference, is a function of wages in this single covariate model, and this is statistically significant, so we can mark that as good. If I do a two-equation model with housing units and wages, so the housing supply difference there, that doesn't really matter, and it's still statistically significant, and wages still matters. And there's some difference between this number and that number, right? 50% difference, but not crazy difference. Then we add another value. We look at total households here. We have, a measure of population. It's not statistically significant. That value is too high, but that wage value is, and it looks very much like that one. So we're seeing a second value. In fact, those are so close together that we would be very confident that those are the same. The problem is we added that extra variable and the significance of the regression went away. And up here you can see how the adjusted R squared, first it went from a 0.2021 up to a 0.033, and now it's being penalized for adding an extra value that doesn't matter. And I skipped ahead, an extra variable that doesn't matter. You can see none of these variables, wage, median age, total households, are statistically significant. All these numbers are much over 10%. They're 62, 97, and 64%. So we're confident that those don't matter. And same thing with the number of housing units, but then wages do. The problem here is, again, like the last one, that's not a statistically significant equation. And so if we're trying to inform policymakers, a boss or something like that, we'd probably be mostly satisfied with that simple model, just two variables. It tells us a little bit more. It but it's not a lot. It doesn't tell us a great deal about why homes are priced the way they are, but it tells us enough that we can, use this for some decision tools. And that's really what I'm trying to do in the statistical portion of this class, is expose you to the type of statistical thinking that you need to have had prior to walking into the MBA classroom. And most of you have had some sort of statistical inference in a class or elsewhere. Be shocked if you didn't. But what you probably don't remember is the fundamentals, how we do comparison of two means. And we know that the values aren't going to be perfect, but we're going to have a way to determine how close they are by looking at their variance, and that we're going to be able to compare the means and the variance using that student's t-test. And then we're going to be able to compare the variance between two sets of variables to see if they vary differently from one another. Even if the means are different, maybe the variation between them is the same, and that can be important in a lot of circumstance. So let's say we're looking at light bulbs, and we have two sets of light bulbs. We care a lot about their average lifespan, but we also care about their variance, right? We want the variance to be very short. We don't want them to burn out quickly or last longer than we offered. And so if we had two sets of light bulbs and one lasted less, but we were confident that all of them are all going to burn out almost at the same time, we could charge a little bit less for that lot than we were at a different one. And those examples extend to selling agriculture or clothing or anything else. And then we use the regressions just as the term regression comes about the idea that if you have variables along a line that there will tend to be a movement towards the average, and the line is the average that we would draw. I talked about that in earlier plotting of graphs. But we really care about multivariate regression because multivariate regression allows us to look at several different variables. And all along the way, we care about the signal value. That's the coefficient here, this highlighted value here, to noise, which is the variance, right? Here, in this case, the standard error. And so we care about the signal to noise ratio, which is the t-statistic. And when the t-statistic is about 2 or approaches 2 or higher, that means we have a higher signal to noise ratio, then we're confident that we can use that value. And if the signal to noise ratio was lower, but it was a big impact, we might also care about that. So, for example, if we're testing drugs and the one lot has a really good signal to noise ratio, and then the second lot has a little bit weaker signal to noise ratio, but this medication kills a lot of people, right? Or even if it had a higher signal to noise ratio, if the effect was much worse, then we would be very concerned about that medication. And so there are instances where this matters. And you're going to learn in your MBA class how to differentiate between a joint variance, which is the F statistic, right? The T statistic was a comparison of variance of means, and a Z statistic, which is used for other applications. Those are different signal to noise ratios. And I want you to be familiar with that when you're going into it, because I think what we often miss in this instruction is just to give you a sort of rule of thumb that you can follow a gut feeling. But again, if you're taking class from someone who's very vigorously statistical, they may just be, very concerned that you follow 1950s style of setting a threshold that you'll accept and living with it, but modern economics has largely thrown that out. And so the test is going to ask you to do this modeling. We haven't done economics, so we haven't started teaching economics, which would teach you how to structure these models. So I'm less worried about what you have as an X or Y value and far more worried about how you execute the statistics here, because this Excel is a basic piece of software that you'll use throughout your business career to evaluate things. And whether or not you're in medicine, anything in management is likely to cause you to need to work on that. And so let's just talk about briefly the exam and what it is you'd want to know. So this is the practice exam. It's the same one I use each year. It's a practice exam, and I'm going to change. I'm going to give you 2 sets of data, and I want you to just walk through the things that I've done in these lectures with each of these, right? And again, I'm not looking for a result. I'm not going to compare your regressions. I'm looking to see that you have created these in a file and posted them here so that I can see them. And so as you read through these, you can see that these tests are going to, this first test is going to carry you up through statistics, right? And then the elasticity, supply and demand elasticity. And that's what we're looking for on this first exam. And so you'll hear from me in or around the posting of this file, how to deal with the individual elements of this, and how to take the exam. If you have any questions, please email me. Thank you very much.